All right. Right, we almost have everybody. All right, looks like we have everybody here. So without further ado, let's get started. Welcome everybody to tonight's Superstellar Friday. I'm glad that you are all able to make it. My name is Amanda Leap. I'm one of our educators at the Discovery Center, and I am going to be our host for this evening. So before we get started and before I introduce Sally, our guest speaker tonight, I just wanted to give everybody a rundown of how the event is going to go today. So throughout this time, you can use the chat feature right along the bottom of your Zoom. So if you have any questions for Sally throughout her presentation, you can just put it right in the chat, and I'm going to keep track of those questions. And at the end of her presentation, we're going to have a Q&A session. So I'll be able to ask those questions that you've had, and she'll be able to cover those as well. So any questions you have, you can pop them right in there. And if you want to wait until the end for the chat as well, you can absolutely do that. But I'm going to pass the floor over to Sally in just a second. So Sally is our guest speaker for this September's Superstellar Friday. She's going to talk a little bit about Hubble's history and the future with James Webb. She's a NASA Solar System ambassador, and we're really excited to have her here tonight. So without further ado, I'm going to go ahead and mute myself and pass the floor over to Sally.
Thank you, Amanda. It's exciting to be here. I just want to say that when I work on a presentation about any kind of mission, I'm always in awe of its own story, because every mission seems to have gone through such incredible teamwork and such, ups and downs sometimes to make sure that their goals are presented. And we use the finest minds in the world to come together to do some incredible things. And I think those kinds of things we need to hear about more and more. So this story about Hubble and its contributions, and then with the James Webb Telescope, is very exciting. So my goal is to go through a little bit of the history in a nutshell of Hubble and its accomplishments, and some videos or some images. And then there's a video that I will show you about how Hubble really changed the view of how we examine our universe. And then, of course, how we're going to a little bit certainly about the James Webb Telescope and how will it extend the Hubble story. So how do we see the universe? We see it through light. Our primary source of light is the sun. All light originates from the accelerated motions of electrical charges. Light is an electromagnetic phenomena called the electromagnetic spectrum. And here we have a diagram of our spectrum. If you see in the center there in the visible light area, that's where our eyes are able to see. We see various objects of the universe because light, here we go. I'm reading the wrong thing. Here we go. We see the world around us as though through visible light waves, which makes up less than 1/millionth of 1% of the measured electromagnetic spectrum. Our eyes can only detect in the visible range. The electromagnetic radiation is all around us. And as you can see, there's higher energy waves and lower energy waves. But we have that small window in there, in the middle of that diagram. And I have another diagram that shows various observatories and their view of the Milky Way. As you can see, Hubble there in the middle. I don't know if you can see all right. And then we have the Chandra. It's an X-ray telescope. And then Compton, which isn't anymore, but it took a lot of gamma rays. at that energy level, which is a very high energy level. And thank heavens, these do not reach our Earth because of our atmosphere. And then the Spitzer, showing at the infrared, and that's not functioning anymore as of this last year. But that gives you a perspective of where these observatories are along our magnetic wave spectrum. And I will have to, I know this talk is on Hubble and it's on the James Webb, but we have 2 observatories currently functioning now, and one of them never gets recognized, and that's the Chandra Observatory. It has its own incredible story, which could be another presentation, but the media doesn't hear about it. And so I just want to give a shout out to this observatory. It's an Xray Observatory, and it has a very elliptical orbit, and it's on the far side of the elliptical orbit, about 1/3 of the way already to the moon. So it has done some significant contributions to the Hubble observations also. So it's a different perspective. So where did this idea come from, this origin of placing a telescope in space? And it came from, in 1946, from Linus Spitzer, who wrote a paper called The Astronomical Advantages of Extraterrestrial Observatories. And he was explaining how the benefits of, if we get above the Earth's atmosphere where it's clear, we'd be able to study more. So then I began to wonder, since science is all about connections, where did he get that idea? He got the idea from one of the 3 fathers of modern rocketry, Hermann Oberth, who in 1923 wrote a book called A Rocket into Planetary Space. And he was a pioneer. And he's the one who said, we should be able to put an observatory, a telescope, into the Earth's, above the Earth's atmosphere. Now that was in the 40s and the 20s. Okay. NASA in the United States really didn't get focused on studying how can we do this? How can we get a large telescope up in space until the 60s? So it took a whole decade for us to get organized from that first paper in the 40s. What happened in the 50s? A very significant event, the dawn of the space age. In October 4th, about the size of a basketball, it weighed only 183 pounds and took 98 minutes to orbit the Earth on its elliptical path. Now, that changed our entire perspective of how we explore Earth and explore our solar system and beyond. And I do have here, if I can find it, a sound of it. Let's see if this works. I'm trying to get it off here. There we go. There. So before Hubble, in the 60s, there was finally a committee formed, and Lionel Spitzer was the person to head it. And they decided to study and research the possibilities of an Earth orbiting telescope. And then in 1969, the committee published scientific uses of a large space telescope. Now, in the 60s, when we think back, a lot was going on. Here we have Sputnik, which was the beginning of the race to space. And so NASA was trying very hard to catch up. I mean, the United States did not want to be behind. And so what kind of programs did we have in the 60s? We had the Mercury program, we had the Gemini program, we had the Apollo program. And I did not know, and this was something I learned, that NASA was able to launch 2 successful orbiting astronomical observatories in December of 1968. Now they did 4 altogether. They launched 4, but 2 were the only ones that were successful. And those 2 were able to make observations. One of them, Copernicus had 4 X-ray detectors, and it also was able to find pulsars. And so those 2 were able to do some exploring in our solar system and to stars. And I never knew that, to be very honest with you. I thought the Hubble Telescope was the very first one to be launched into space. In fact, I even thought I read that, but maybe it was the first large one, but it wasn't the first. So that was interesting to find out. How did the Hubble project become a reality? In the 60s, NASA started, and they had a lot of failures, but along with their successes, they really started getting serious about studying this program, and they also started the development of the Space Shuttle program. And so in the 1970s, they proposed to put a 3-meter space telescope, but you have to get this approved by Congress, and so it was turned down. So now what? Just like in many missions, when they're turned down, and many of them are, we have to go back to the drawing board. And so this time NASA invited the European Space Agency to participate. That would help with funding and also create an international effort. And the mirror went from a 3-meter to a 2.4 meter, and that lowered the cost from anywhere from 5 to 400 million to 200 million. The proposal was finally accepted by Congress in 1977. The launch, fuzzy photos, and a spectacular repair. The original date for the Hubble launch was in 1983, and that was delayed. But during that year, 2 interesting things happened. The founding of the Space Telescope Science Institute at the Johns Hopkins University in Maryland was founded, and that would be in charge of the Hubble research. And then the naming of the telescope after Edwin Hubble, who did extensive research on stars and galaxies. And I have a slide later on in the program that talks a little bit more about Edwin Hubble. So the next date, of course, was for the launch was October in 1986. But tragically, that was definitely delayed because of the January 26th disaster in that year, the Challenger, which took the lives of our dear astronauts. Finally, Hubble was launched on Discovery in April 24, 1990. But the first images came back on the fuzzy side. So since this was a mission that was to be serviced, to be upgraded, the engineers in the 3 years that they had before the first servicing mission had 3 years to go ahead and figure out how to fix that mirror. So if we think James Webb had a lot of delays over the years, I guess so did Hubble, and a lot to contend with. The servicing missions. The first one in December of 1993 was to mainly repair the primary mirror. And then in February of 1997, they added some new instruments. In 1999, in December, they put a gyro replacement, and that was critical because the fourth gyro out of the 6 needed to be replaced, and that balanced the Hubble. And so when that wasn't working, Hubble went into what they call safe mode. All the missions, any of the spacecraft that goes out, if something doesn't go right, it will go into safe mode until the computer and they can get it corrected. And I find it amazing how we can put something into space and we can communicate with it. And that's through our radio waves, and we can adjust things, which is pretty cool. And the last servicing mission, 2009, it really did a lot of advanced instruments. So it was almost like it was a whole new telescope. It was reborn. And these are some of the images of some of those servicing missions, which are exciting. This could be a whole presentation unto itself, and how they learned and how they did this, which I find pretty fascinating. Hubble images. This is comparative. Now, in the last service mission in 2000, it was in December. Okay, so this first image on your left was taken in November of 2009. Then they repaired it, and this was taken late December of 2009. Now, what I realized again, that even though the images were fuzzy, while Hubble was up there still took a lot of images because they could still study fuzzy images. I thought that was kind of neat. 3 facts about Hubble. Hubble travels at the speed of about 17,500 miles per hour, which covers now the distance equivalent to a trip to Neptune. Hubble has peered back into the very distant past to locations more than 13.4 million light years from Earth. And its mission began in 1990. Hubble has made more than 1.4 million observations. Further contributions on Hubble's part to science is Hubble helped pin down the age of the universe, now known to be 13.8 billion years, roughly 3 times the age of Earth. It discovered 2 moons of Pluto, Nix, and Hydra. It helped determine the rate at which the universe expands. And the universe, they're finding, either goes faster or it slows down. And it was surprising that there's different rates over time about how the universe is expanding. It discovered that in every major galaxy, there probably is a black hole that anchors it in the center. And it created a 3D map of dark matter. It also characterized the atmospheres of planets around other stars. It monitored weather changes on planets across our solar system. There have been over 7,000 peer-reviewed scientific publications, and there will be more because there's a lot of data. Its archive archival data alone will fuel future astronomy research for generations to come. Hubble almost put a Pandora's box out when he felt that there would be, he used this Hooker Observatory in Mount Wilson, and he went ahead and wondered if the universe was expanding. And so it opened up this Pandora box of debate. And so his findings and his observations led to the fact that we have a telescope named after him. This is a video. It's about 6 minutes long, but it's very special. It takes you back in time. There was a time where the astronomers decided to take a dark patch of sky, and Hubble pointed at it and looked at it for 11 days. So this video is like a journey in time. There's no narration except through words at the bottom. And it takes you way back to where galaxies were first formed and what they look like. And it shows you the evolution of a galaxy and how it develops. I hope you enjoy this, and I hope the bandwidth will allow this to happen. I knew there would be an advertisement. There we go. I always have to pause when I think about,
The truth is that Hollywood's elite actors
okay,
can get
I,
ripped while adding 12, 15, even 20 pounds of muscle in just a few weeks because they follow a long forgotten and suppressed by the fitness industry secret.
okay, so now that we're able to stop that other video, which I didn't do, then what I'm going to do is try to get back to my PowerPoint. Exit full screen. Okay, so I have to go back here. Sorry about that. As much as we rehearse this. Anyway, I just have to take a pause to think about our place in space and how even our solar system within this little patch is so tiny, and that Earth is like an atom, and so it just really makes one think about what's out there. It's pretty amazing, and what they did with that video is very striking. Hubble has been, last year had its 30th birthday, and so this image was released on its 30th birthday. It's nicknamed the Cosmic Reef. It's a red nebula, and its smaller blue neighbor in the left corner there is a star-forming region, which is in the large Magellan in the cloud. And it's very significant. It's a satellite galaxy of the Milky Way. It's located about 163,000 light years away. And it's a very striking centerpiece of bright, hefty stars, each 10 to 20 times more massive than our own sun. And before we go on to the James Webb Telescope, as the Hubble Space Telescope continues to deliver compelling science 30 years after its deployment, it's important to acknowledge some key contributors to the mission's success. As NASA's first chief of astronomy programs, Nancy Grace Rowan, who died and passed away in 2018, shepherded some 20 spaceborne astronomical missions in the 1960s and 70s. Her longest lasting effort was to help establish a large diffraction limited orbiting space telescope, an instrument to which took several names before it became Hubble. Today, Rowan is warmly remembered by her colleagues and followers as one of the central players who turned the decades-old dream into a reality. The James Webb Telescope, which is going to be launched this fall, hopefully. It's a large infrared telescope with approximately a 6.5 meter primary mirror, launching hopefully in this fall. Its mission is to seek light from the very first galaxies of the universe and to explore distant worlds. It's to be used by thousands of astronomers, and it's led in partnership not only with NASA, but the European Space Agency and the Canadian Space Agency. Now, who's James Webb? He was very instrumental in the 60s with all the programs that were happening during that space race, when Sputnik decided to alert everybody to we're on board. And so the United States doesn't like to be last. We want to be first. So the competition was there. So he was instrumental in running all these programs, the Mercury program, the Gemini program, the Mariner program, along with the Pioneer program and the Apollo program. And he also insisted on a long, very hard, strong science program. So that's who he is. He was the administrator of NASA from 1961 to 1968. So let's compare these telescopes. All right, the mirror on Hubble was 2.4 meters, which is 7.9 and feet, and the James Webb is going to be 6.5 and 21.3 feet. The length and weight, the length 44 feet for the Hubble and 72 in length for the James Webb. But notice the weight. The Hubble weighs 24,500 pounds, whereas the James Webb is, even though it's longer, it's going to weigh 13,500 pounds. What a difference. That's significant. The wavelength instruments that they're going to have, Hubble has visible and near infrared, whereas the James Webb is going to have also the visible, near infrared, and the mid infrared. And the temperature for the James Webb is extremely cold compared to what the Hubble's, which is Hubble is at 70 Fahrenheit, and the James Webb is going to be kept at 370 Fahrenheit. This is a diagram that shows on your right, you have your part of your electromagnetic spectrum. You have your visible right on the top here, and then you have your infrared, near infrared, and your mid infrared and far. The limit of Hubble's, with all what he could see, was right there at the near infrared, whereas James Webb will be close to the near. So it's really going to stretch and add to Hubble's story by looking further into time. What powers the James Webb Telescope? There's an electrical power subsystem that provides electricity to the subcraft, and this consists of solar panels, rechargeable batteries, a solar array regulator, a power unit, a telemetry acquisition unit, and the solar panels will convert sunlight directly into electricity. This is another view of the electromagnetic spectrum, and it shows you three observatories. It shows you the Hubble, and it shows you where the light in the visible and going into the near infrared. Here's where the James Webb and how they're overlapping, and it just shows you also Spitzer, which is not functioning anymore, was into the far infrared. Hubble is located 350 miles above the Earth, and James Webb is orbiting the sun around at Lagrange 2. Now, Lagrange means a balancing point. If you have an orbit around a body, there are certain points in that orbit where the gravity pull and push is equal or even. And many missions use that Lagrange point to save on fuel. So And this will take about a month for when James Webb is launched to get to that Lagrange point in the orbit of the Earth. There are two main innovations here. The two most striking would be the primary mirror and your sun shield. The sun shield, it protects the telescope from heat and light in the sun, moon, and Earth. It's about the size of a 20-car parking lot. It consists of 5 layers, which are very thin, like plastic wrap. And the layers do not touch each other, and the coatings of aluminum help cut down on the warmth transmission. And this is a diagram showing you on the hot side, the light from the sun and the burn of the moon, how hot it would be in the solar panels, the communications, and the bus part of the spacecraft is on the hot side. You have your computer and your steering and your reaction wheels and jets. And on the cold side, you have your sun shield and your mirrors and your scientific instruments. This is another video that shows how things, when we look around us and we use different things, how they come together. There's always a connection. And so the Japanese art form origami has been used in designing spacecraft, and it was very instrumental in designing the James Webb. It'll also show you other kinds of missions that the origami has been used in, which is really kind of cool. In this video, it talks about the launching of James Webb in 2019, of course, which did not happen. So anyway, here's a short video showing you how origami was used.
Whatever big thing you're working on, don't feel paranoid. Only you can see it.
Origami is the ancient art of Japanese paper folding. For years, it has been used to create stunning works of art. But origami has also been used in more surprising ways, like car airbags, stents, and even space exploration.
What we want in space are large structures, not necessarily massive, but large, which means you can make them out of thin materials. And wherever you can make them out of thin materials, you can use origami to fit them in these rockets.
Many space projects have used the folding principles of origami. The solar array wings on the ISS use a Z folding pattern, and the Mars Phoenix lander used a fan-folding solar array called the Ultraflex.
Because the biggest rockets we have right now are only about 5 meters in diameter, we have to come up with a way of folding up this very large structure into spaces that we can launch it inside a rocket. And once it gets to space, it can unfold itself. And origami is one mechanism by which we can do that because it gives us the underlying mathematics of how large, thin sheets fold up.
One origami project currently in development at NASA's Jet Propulsion Lab is the Star Shade, which is essentially a big star blocker. Have you ever tried to take a picture of someone when the bright sun is beating down on them? All the detail gets washed out. This is the same problem astronomers have when trying to image exoplanets. Currently, astronomers detect exoplanets indirectly using a shadow technique called the transit method. For an Earth-sized exoplanet orbiting a sun-like star, they can't be imaged in detail because the stars they circle are much brighter than they are. This is where the star shade comes in, to help block that bright light to better help astronomers learn more about these mysterious planets and look for biosignatures for life.
One of the ways in which we're thinking about suppressing the starlight is using something called star shade, which is a very large external occulter that flies in front of a space telescope and blocks out that starlight so you can image that really faint planet right next to it.
Sounds easy enough, but the starshade is roughly the size of a baseball diamond.
Because the starshade is so huge, we have to come up with a way of folding up this very large structure into spaces that we can launch it inside a rocket. And once it gets to space, it can unfold itself.
Which is where origami comes in.
So this is one of the candidate fold patterns that we had for the inner part of the starshade, what we call the optical shield. It's got a very deterministic shape when it's folded up, so we designed it to have this shape in which it can account for the thickness of that blanket. You can mathematically define how this sheet of paper is folded up, and the way it unfolds is like that it creates these very nice spirals inside the folded structure. It's quite remarkable in its simplicity.
This giant space flower may seem simple in design, but not in implementation. The starshade will need to unfold with millimeter accuracy. Once opened, thrusters will move the craft through space, positioning the starshade between the star and the space telescope. With the star now being shaded, the telescope can image the planet in detail to find out whether conditions for life exist. Origami has been practiced on Earth for years, and scientists will continue to draw inspiration from it to help package big space structures more efficiently, from solar sails that use sunlight for propulsion to sunshades for telescopes like Gaia and the James Webb once it launches in 2019.
We can take these ideas from origami and apply them to spacecraft structures that way.
Because when it comes to the future of space exploration, if we want to think big, we also have to think small.
And also to add to that, these mirrors are coated in gold, and a very, very thin layer of gold. And if you took all of that gold together, it would probably be the size of a golf ball. So the Webb will be launched from a French Guiana, which is a little country in South America, from Ariane 5 rocket in the late fall. And it's about ready to, it's in California now, and it's passed all of its tests. So it's going to take a journey, a slow journey, to get to the French Guiana country. Now, I pulled this back. This is on both Hubble images, and I put this in here to show the difference than what can be with your infrared. The image of the pillars by Hubble was in the visible light range. And then the one same image, only this is in the infrared that Hubble revisited. And look at the difference. So when James Webb look at that, probably that same image, it will even go further. So it gives you an idea that we're going to be in more depth. And so the last video we have here talks about the James Webb Telescope.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe, and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sun shield ever flown. A 5-layer, tennis court-sized sun shield that blocks heat from the sun, Earth, and Moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
So it will take about a month for it to get into the Lagrange point, and a very long period of time for it to cool down to get to that level where it can take images. And it will be about 200 days before the first images come. And I want to thank the various people that helped me be able to put this together. I took two webinars, and so we have the first four people listed there were on that webinar. And I have 2 friends who are encouraging me and giving me all kinds of advice from Nevada and Hawaii. And then David McDonald is the person who got me involved into presenting today. And also I can't thank Amanda and Mirka for their technical help. So I want to thank them. And this was fun to do. And so that's the presentation. And if you have any questions at all.
Thank you so much, Sally. That was wonderful. So now we're going to open up for a question and answer portion. So if anyone has any questions, now is a great time to type them up and put them into the chat. But we do have a couple of questions to start with. So for the Hubble images, when they were taken, are those taken in color already, or how do you get those colors from those Hubble images?
Any of the telescopes that when they take images, they're not taken in color. The scientists apply the colors through filters, and they use a red, green, and let me check here, and blue. at different exposures, so that scientists apply the colors because it will emphasize certain areas at different wavelengths so they can study them. So the images that come down are not in color at all. It's the scientists who apply that color. Like your X-ray images from Chandra, none of them are done in color. We add the color to give us the experiences. And if you put different colors, it will emphasize different things, and then they study them different ways.
Excellent. And then another question is, what exactly is a NASA Solar System ambassador, and how did you become one?
Oh, I applied to this program, and there's about, I would say, maybe 1,000 throughout the United States of solar system ambassadors. And our job is we take training and different webinars on different subjects and different missions and present to audiences to become aware of what's going on. And it's very exciting because there's a lot of neat stuff that people aren't aware of. And it's not a paying job. It's simply something that we do to volunteer, and we try to work together many times and try to, there's about 3 solar system ambassadors in New Hampshire, I believe. And so that's basically what we do. I'm a retired teacher that still keeps presenting and still keeps learning. And I want to keep going.
Excellent. I love to hear that. So then another question, will we be able to physically repair the Webb telescope like we have the Hubble?
No, it's not a service. The only observatory that was able to get repaired was the Hubble, because it was close enough to Earth, and that we had the shuttle program to capture it so that we could fix it. So whatever happens, what they'll do is, if something goes wrong with Hubble, I'm sure it'll go into a safe mode and they'll make adjustments. And they've done that with different instruments or different missions, I think. Were they able to do that with the Compton Observatory? I'm not sure. When that ran out of fuel, I think they just had that plunge into, I think, the Pacific Ocean. They want to control when something is close to Earth and it's not working well, or it's finished its job, then they try to control it. If it's way out in the far reaches of our solar system, then it just stays there if they can, but they want to control things. So they'll just have to do it safe mode, and then just like the Perseverance or the different rovers that are on Mars, when they go into safe mode and they have to reprogram the computers to adjust to see if they can get them out of that situation. Like for Spirit and Opportunity, they did the same thing until it ran out. And all of those missions on Mars have already, except for the Perseverance, who just have gotten there, so it's not an extended mission, all went beyond their lifetime. They went on extended missions for a long time, so they really did their job. And it's amazing to me that you take something so far away, and yet from here, the people working on it can send a message and figure out what it's going to do, even though there's a delayed time, and they can just reprogram it so it can hear it and do it. It's totally amazing.
Awesome. So we have enough time for a couple more questions here. So a couple more questions. Where will this data from James Webb be where will it be sent here on Earth? Where will those transmissions be received? And also, what are the size of the images that Webb is going to produce in terms of megabytes, if you are aware?
Oh, I'm not sure. I think it's the outfit that's the academy that's in the institute is going to be in charge of the data. So I think different astronomers are going to put proposals in, and they're going to, have time on that telescope to use. And so that's when they said it's your telescope, it's your, and I'm not sure exactly whether the Deep Space Network is involved with that, which is a series of radio telescopes, 3 of them, one in California, one in Spain, and one in Australia, I believe. And they're the ones who gather the information and then transfer it all to the prospective areas. And I think it's in Maryland where it's in charge. No, that's the Hubble. So that's a good question. I'm not sure where the head people are for controlling that and where it's going to be.
I'm sure we'll have more information on that as we get closer to launch, and then once it's up.
And then I can research that too, and then we can add that. So
yeah, perfect. All right, and then one final question. The James Webb has taken a long time to get ready for launch. And what is the cost that this telescope is going to produce at the end of its mission here?
Cost as far as
how much it costs to build and then to launch as well.
The money piece. That is another one that I don't know. It probably cost an incredible more amount of money because of the continued delays and because of the complexities of the engineering to get a huge mirror stacked and tucked into a smaller spacecraft. So that's another one I don't know.
Yeah, I know I read somewhere that NASA had stated they are years and billions of dollars over budget. So I'm sure we'll have more information. Yeah.
And so, not all of that had to be from NASA or from the United States, but a lot of it was. So because you've got 3 agencies that are involved in it. So it's a shared debt. So
perfect. All right. Well, I believe that is the time that we have today. Thank you everybody for joining us. And a very special thank you to Sally for putting this presentation together and being here with us this evening. I'm going to go ahead and end the Zoom tonight. So I hope that everybody has a great evening and a great Labor Day weekend. That you all stay nice and safe. And if you're able to, come out and join us tomorrow at the Discovery Center for our Aerospace Fest. But I hope that you all have a great evening. So thank you for coming.
Thank you, Amanda.